As I said, and as Jack mentioned, I'm a nuclear physicist. I do mostly work in particle physics, trying to connect particle physics and nuclear physics. And what I'm going to talk about today in the software side, I've been working with Ken McElvain and André Walker-Loud, who are at a combination of UC Berkeley and Lawrence Berkeley National Lab. Myself and Gustav Jansen, who was our Insight liaison for work that we did on Titan at Oak Ridge. And the software that I'm going to talk about today, there was like a baby proof of concept version that we actually got a lot of use out of in production that we call MetaQ, and then the actually, hopefully, high quality software that I'll go into a little bit of detail about, which is MPIJM. Good, so a little bit more about who I am. This is what I like to think about. I'm a physicist. I'm mostly interested in big computers because I care about physics and not computing itself. Computing to me is a means to an end. And the thing that I like to think about, so here's my picture of an atom, and if you zoom in on the atom, you wind up with the nucleus there in the center, and it's made out of protons and neutrons. And if you inspect protons and neutrons even more carefully, what you find inside are quarks and gluons, and that's the place where people usually go, I didn't learn this in high school. And so what that means is if you know enough in principle about the theory of quarks and gluons, you can predict everything there is to know about nuclear physics. And the theory of quarks and gluons has been known since 1972, and it's still an outstanding problem to do really anything quantitative to connect the two. So that's the thing that I'm interested in doing. And there's a lot of open questions, surprisingly, about very simple nuclear physics things. So you may have heard, it was in the popular press, that there's this puzzle about the size of the proton, different ways of measuring give different answers. And these are the things that I'm really interested in. I'm interested in consuming as much supercomputing power as I can in order to answer these kinds of questions. And if that means I have to write software, then I will. But if someone else could write the software, I would be happier. So what kinds of questions are we interested in answering? One recent result that I was involved in involves the decay of neutrons into protons. If you just take a neutron and let it sit there, after 15 minutes or so, it decays into a proton, an electron, and an antineutrino. And you can measure the lifetime of a neutron, so it's about 15 minutes. And we know a formula that lets us calculate it, and it has this parameter, GA, which essentially describes the strength of this interaction. And if you go and try to measure this number in two different ways, one by sticking neutrons in a bottle, and one by shooting them in a beam down some kind of detector, you find two numbers that aren't compatible. And so the question is, can we calculate this number so we can get a good handle on this number and try to discriminate between these kinds of results? And so the thing that we do in order to address these kinds of questions is something called Lattice QCD, wherein we take all of space-time and chop it up into a grid and use that grid to calculate with the theory of quarks and gluons in order to produce nuclear physics. So the kind of problem that I'm interested in solving, it looks like a horrible integral. This is an infinite number of variables that then I will take space and time and chop it up. So now I have a still horrible but now finite dimensional integral, an enormous dimensional integral. And the thing I'm going to do is I'm going to put my gluons on the links and the quarks on the sites, and this is just background for education. And the strategy for doing these calculations is to use this thing here as a probability measure, and the observable that we're interested in calculating, we generate a big Monte Carlo Markov chain, and then measure the observable that we're interested in on every one of these samples in the Markov chain. And we know that if we do this enough, we get an answer that we can rely on up to statistical effects. So if you let me spend more money on computing time, I can get a better answer, guaranteed. Right? That's a nice problem. It doesn't require machine learning. It doesn't require. It's very well posed, definitive problem, and yet to do anything nuclear physics related really is going to require exascale computing. That's where observables that we've been interested in forever sort of become unlocked. Okay, and so the kinds of things that we want to do in our calculation involve linear solves. This is essentially, we want to find out how a quark goes from one place in space-time to some other place in space-time, and that requires solving this linear system where this D/matrix is some nearest neighbor sparse matrix. Okay? And with the results of those, we want to do tensor contractions. So we're going to take this propagator that tells us how the quark goes from here to everywhere, and then tie it up into something that looks like this. And there's 3 because a proton has 3 quarks inside. And these are really the main numerically intensive steps that we're interested in solving. And there are very good software packages written by the community with help from NVIDIA that let us do the linear solves on GPUs. So that's exciting, and that's great because I don't have to understand how it works. I can just ask it the answer, something goes onto the GPU, crunches away, gives me the thing I'm interested in. And this step is more application specific, and so this does not tend to be so nicely optimized by colleagues at NVIDIA, and so we have to do this, and that means it typically winds up on the CPU, because we don't have the manpower to program new application kinds of things every time. Once we do that, we do it, one time we get one number, we have to repeat the whole process a large number of times. Because we took space-time and we chopped it up, we want to make the chopping finer and finer until the grid disappears from the effects of the simulation. We want to tune the parameters so that we get results that reproduce things in nature. And we want to take the box and make it bigger and bigger until it stops affecting the result. So controlling all of these systematic things mean that we have to simulate on many, many different ensembles. And you get a result that looks something like this. Each one of these points is the result of a large Markov chain Monte Carlo thing. And the result that we achieved is this purple band. And the physical answer is the purple band intersected with this gray band. So this is our final number for this quantity GA. The experiment is here, right? And so we have a 1% uncertainty. The experimentalists get a 0.1% uncertainty. And how are we going to shrink this down? We need a lot more computing power. And we're going to need to fill in points sort of all in here, and this is going to be very expensive. And how can we get this calculation through the machine? These calculations I'm describing were done on a combination of computers. The biggest workhorse for us was Titan at Oak Ridge. We also used Edison, which is a Cray machine at NERSC, which is at Lawrence Berkeley National Lab, and Surface, which is an NVIDIA GPU machine at Lawrence Livermore National Laboratory. And of course, going into the future, we're excited to be able to use these machines. Summit, of course, you're probably all familiar with. It's the new machine at Oak Ridge. There's also Sierra, which is the same machine idea at Lawrence Livermore National Lab, but instead of 6 GPUs on a node, it's got 4. And then there's a smaller machine, also at Livermore, called Lawson. And this is the machine that we'll probably be using at Livermore. This machine is for weapons design this machine is for science. Good. So a little bit about the machines. I cribbed all of these numbers off of the website, so that I can't explain anything in detail about how any decisions of this were made. But you can see Summit, it's got close to 10,000 Power 9 nodes, each with 6 NVIDIA Volta 100s. Sierra's got 4, and Lawson is exactly the same, it's just a smaller number of nodes. Okay. Yeah, so this is the future of where this Lattice QCD technique is going to be used. And the issue is the problems that we're interested in solving, we can't use 10,000 nodes. 4,000 nodes, sorry. It's too big. The problems that we've been solving, in order to get this number with 1% precision, we needed thousands of linear solves. Each one takes 32 nodes with all the GPUs on Titan. And we needed thousands of tensor contractions. It took 8 nodes each. It doesn't make sense to try to use 1,000 nodes on a single calculation because you wind up taking the lattice and chopping it up into pieces that are too small, and you spend too much time communicating. That's the main problem. So we need to keep the individual problem sizes small. Dense nodes are actually great for that, but it means it's, except sort of in the naive way, doesn't scale up to thousands of nodes.
Question.
Yeah.
So if you had a 32 node machine of this character,
Mm-hmm.
And you had it to yourself, how long would it take you to solve the problem?
A long time.
Is it an impractically long time?
Yes.
So you actually do need such a big machine.
Yeah, well, sorry. What I mean to say is, for any individual instance of any individual step, it does not require machine scale resources.
Could you publish that individual run in a peer-reviewed journal?
Absolutely not.
Yeah. So you actually do need such a big machine.
Okay, well, I'm glad to hear that that's what you think, because that's what I think too.
Yeah.
And yeah, these kinds of ensemble or statistical runs, it's not the same as, you know, some machine learning applications. Well, when you get 1,000 nodes, suddenly you can learn something new because everybody's working together and crunching a problem that could not, it doesn't fit in 200 nodes, but it does fit in 1,000 nodes, so I need 1,000. That's not our kind of problem. Our kind of problem is we're going to need thousands or tens of thousands or hundreds of thousands of small tasks that we're going to try to push through this machine as effectively as possible. Right. And I can't do that on my little cluster in my office. Right. It's too big. It's too much data, it's just too much all around. Any individual thing is small, but the net size of the problem is big. Yeah?
Let me ask a very unpolite question.
Of course.
Is this not ideal for quantum computing? I know I'm opening a
I mean, if you have a working quantum computer, I'm interested in playing with it. There are problems that I want to solve today that are pressing experimental questions today. And I can't afford to wait 20 years. It'll change the course of, you know, what the Department of Energy decides to fund in terms of experiments or whatever. Right? So the course of learning all of physics can't wait for quantum computing. There are aspects of this problem where even with this numerical technique, we don't know how to do it. And it has to do, there are technical issues with going to high density. So if you want to study, for example, nuclear matter in neutron stars, you can't use this numerical technique, or at least no one knows how. The Markov chain doesn't converge. There's an imaginary part in the weight, so you can't use it as a probability. It becomes a very challenging problem. And that kind of thing is ideal for a quantum computer. Of course, I know how to build a quantum emulator of this system. I just take a proton and look at it. Proton is quantum mechanical. It's got exactly the right properties to tell me everything about a proton. But we just call that doing an experiment. So the thing I'm interested in doing is getting as much computing power out of these machines as possible. And we wind up with, finite size allocations and have to understand what can we do with these allocations, right? And one thing that is common at these large supercomputing centers is that if you can ask for big allocations on the machine, you get a steep discount on how much it costs you in terms of your allocation time. And the reason the supercomputing centers do that is it's much easier to schedule and much easier to queue large jobs. Right? Plus, I think they like to show on their website, oh, this job used 1,000 nodes, it wasn't possible, right? But as I was saying, that for us, using 1,000 nodes really just means gluing a bunch of 32 node things together. At NERSC, you get a 40% discount if the jobs are larger than this number of nodes. I don't know how this number was picked. Okay. On Titan, you got an increased priority in the queue by a week, I think, if your jobs were larger than this number. On Summit, I don't know what the policy will be.
We haven't said it yet.
Yeah, right. So that's why I have a question mark here. But presumably, it'll have the same kinds of incentives where you get a steep discount if you say, I'm going to use a big fraction of the machine for 12 hours. Good. So as I was saying, we have linear solves. We do them on the GPUs because it's perfect for the GPUs. We have thousands of these tensor contraction operations, and we do them on the CPUs. And the one difficulty is that they're done in different executables, and it's hard to get these things if you just use the job submission stuff to run simultaneously. That is, the thing that's really powerful about these machines is that they've got amazing GPUs. I want to use, any second that I have the node, I want to use the GPU at 100% all the time. Right? And so it's kind of a waste to spend any amount of time on a node with these enormous GPU resources doing these tensor contractions in the CPU. And so what I want to be able to do is say, all right, these nodes use your GPUs to do linear solves, and at the same time use this other executable to do tensor contractions on the CPUs without interfering with each other. That's, if I can get them to play nicely, I'm going to have a good time, because the cost of this is going to be completely amortized. It's going to be 100% hidden by this. This 1% calculation, I should say, it used about 180 million Titan core hours, plus I think about a third of that equivalent resources at Lawrence Livermore National Lab. So as I was saying, these are large calculations, and my advisor always told me never to calculate the cost in dollars per paper, but it's large. Okay, so what was our initial strategy for trying to do these kinds of calculations? Well, we have a bunch of similar tasks. Let's just start them all at once. Each one of these tasks, I think, was 4 nodes, and we wanted to make a job that was 256 nodes in order to fit into the batch scheduler somehow. And so we said, okay, 256 divided by 4 is 64, so just start 64 linear solves. You do these, you do those, etc. And what we found was, just because of the natural variation in problem difficulty, that is, some instances of the problem are easy and some instances of the problem are hard, if we did that, we wound up wasting a lot of time. So white here means the nodes are sitting idle, blue means they're doing something productive. And so if you get an ensemble run where one guy sticks out, you can wind up wasting an enormous fraction of your time, right? And that hurts me. I want to get every piece of science out of this machine as I can, and this is a 25% across the board cut. So not only do we have that kind of a problem, I said, we have different ensembles. We have to repeat the whole calculation many times with different parameters. We want to run all of these points simultaneously so that we're sort of advancing science on all fronts and getting to the answer sort of in parallel as quickly as possible. And blue comes from one set of parameters and green comes from another set of parameters. These are both linear solves in this case. And you can see the green one is just easier, right? And so this is a case where the green ones, they don't have anybody that sticks out too bad. If it were just green, there wouldn't have been much waste. And if it was just blue, there wouldn't have been much waste. But because I have a heterogeneous mixture, I wound up wasting a lot of time in these interstitial things here, right? And so just a ballpark is that we wound up wasting 35% on this particular instance. And so what we started doing was trying to do backfilling, essentially like what the batch scheduler on any of these large machines does. That is, we say, well, we know we have some jobs that take 2 hours, some jobs that take 3 hours, and then we've got a bunch of these little dinky jobs. These ones happen to be tensor contractions or whatever, whereas these ones are the linear solves. And we asked for 6 hours, and these nodes went along. They finished their solve at 3 hours and 10 minutes or something like that, and then said, well, in the 6 hours, I don't have enough time to do a linear solve. Let me go pick up work for the tensor contractions where I can still do something productive, so at least I'm not wasting time. And so this kind of strategy helped us have large jobs so that we could get through the batch scheduler, the queuing system, quickly, but not take a big hit on efficiency. Good. So we had a big improvement in terms of the amount of wasted idle time. We found sort of on average, we went from about a 25% waste to a 5% waste. And this is equivalent to a 20% across the board software speed up. So that, to me, means projects, instead of taking 5 months, they take 4 months. And that means I can write a paper in 6 months instead of 8 months. And that means I can try to get a job somewhere. So that's the thing that we're accomplishing by doing this backfilling of computational tasks. The production for this project used essentially a fancy set of bash scripts in order to manage which tasks are going where, right? And so if you have a batch scheduler, such as Slurm or PBS or the LSF thing on these new IBM machines, you write a script, you submit the script to the batch scheduler, and it picks it up and figures out where on the computer it's going to stick this thing, right? And so what we had were job scripts, that is, describing, I want this many nodes, I want to run for this amount of time, I want to do these kinds of tasks, anything I can fit in there. This gets submitted to the batch scheduler. It doesn't know anything about what actual tasks it's going to do. Instead, it looks through the file system, or you could use a database here or something, and says, okay, do I have enough time for this task? Yeah, okay, start it. Do I have enough time for that task? No. Okay, skip it. Go through like this and fill up the allocation provided by the batch scheduler, doing tasks that the users provide. And so we really liked this because we didn't have to change our binaries at all. And we didn't even have to really change our workflow. Before, we were writing bash scripts that got submitted to the batch scheduler. Now we write bash scripts that get stuck in some directory somewhere and get picked up later. So everything was sort of transparent and easy to adapt. But there were Yeah, okay. Good. There are some drawbacks to this kind of system where we're going through you know, a bunch of files considering what work we want to do. And probably for us, the biggest one is that there's no guaranteed way to do this GPU-CPU overcommitting, where this executable go on the GPUs, this executable go on the CPUs. This is a policy-dependent question, and at Oak Ridge, actually, it's not possible to do this. On the machine at Livermore, this machine Surface, we were able to start GPU jobs and then on top layer CPU jobs, and that completely cleared out the cost of the CPU jobs. There are some other drawbacks, which is we had to actually walk over the file system and look at these individual task scripts, and this can be slow and disk intensive. And then finally, probably the biggest drawback was that this bash script that's sort of coordinating the whole calculation runs on the head node. That is, it's run by the batch scheduler. And this can stress common resources that are shared between all the different users. So if I wanted to scale up to 2,000 nodes or something like that, I would wind up spawning a lot of processes on the head nodes. And this caused problems. And if you look at the Titan user manual, there is this warning now. On Titan, each batch job is limited to 200 simultaneous processes. Attempting more than the limit will result in a no space left on devices error. And that's because we crashed the machine. So people at the Supercomputing Center said, what are you doing? Don't do that. And nothing we did was explicitly prohibited, but it was not a model that they had ever had any user try to do before, and it caused a problem, right? And it didn't just affect our calculation, it affected other people's work. And that's really a big no-no. So we want to solve this kind of a problem where even if it's not easy to put GPU tasks and CPU tasks separately, we can still do it. And we want to solve this kind of a problem where we know that we're never going to screw anybody else up. Those are the real things. Good. So, what's the solution that we've been working on for some time now? The solution is this software that we've been writing that's called MPI-JM for Job Manager. And rather than being Bash, it's C++. It's, I don't know, it's less than 1,000 lines, maybe 1,500 lines, I think. The job management is done on the compute nodes. It's done on nodes that the computer already gave to you. So you know, even if you're going to cause a problem, you're not going to cause a problem for anybody else. You're only going to hurt yourself if you do something irresponsible. And it lets you take individual executables and launch them on individual input parameters, specifying I want these GPUs on these nodes and those CPUs on those nodes, and mix and match. You can say how much memory your application is going to use, and you can figure out, okay, I can take these two independent tasks and stick them on the same node. They're not going to interfere with each other. They're not going to cause a problem, right? And that helps amortize the cost of everything. And finally, we have integrated a Python front end with pre and post hooks, so that when your calculation is finished, you can go and do some cleanup or something like this, but you can write it all in high-level stuff and don't have to worry too much about integrating those kinds of things into your executable.
But is this running on top of the batch scheduler, or is bypassing the batch scheduler?
I'll explain what it's doing, I think, on the next slide. Nope, 2 slides. So, in order to use this software, what do you have to do? You have to include the header file that tells you how to connect. Okay, you have to link against this little library, the worker library. After MPI init and MPI finalize, you have to do a handshake. So this is 2 lines of code, something like that. And what this handshake does is it disconnects the MPI communicators from of the individual application with the daemon that's running on every node. And this is necessary because if your application crashes and you haven't disconnected the MPI communicator, then everybody goes down, right? That's an insane but part of the MPI specification, right? So in order to say I'm going to have a robust calculation that is not going to give up my whole allocation just because someone put a semicolon in some input file somewhere, I need to disconnect the individual tasks from the main management system. The finalize, reconnect, gives some exit status kind of information, disconnects and dies. And then the daemon says, okay, I'm ready for more work. Once you make these modifications to your software, the binary works with or without the job management stuff running on top. And that's great for debugging, for example. And this slide I lifted from a talk to more Lattice QCD oriented people, and so they were interested to hear that we've already integrated it into the communications layer of the community Lattice QCD software, so that anyone building on top of this all sorts of physics applications, they don't have to do anything. They just configure with one new flag, and it just works.
It's 5 minutes.
5 minutes more, or 5 minutes, I blew it.
No. It's
okay.
It's 9:40.
Yeah, good. Ooh. So, what is it doing, right? You ask the batch scheduler for some number of nodes. In this case, okay, it's 32 because I have to draw a pretty picture where you can see what's going on, right? And the first thing that happens is that a little daemon gets spawned on every node. And this is measuring, it's responsible for launching the tasks that you're interested in doing. It's monitoring PIDs to see if your job has died, things like this. Okay. And on a single node, typically on the MPI rank 0, we launch a little scheduler. And this is the guy with the Python front end, and it's going and deciding, okay, how much work do I have to do? These tasks are GPU related, these tasks are CPU related. How can I layer these guys on top of each other in order to get a good thing? So what it knows is I've got 4 blocks of nodes, which I picked in order to make sure that the communication between them all is good in some way. You can measure the communication ahead of time, for the whole machine, and store that wisdom. And say, okay, I have a block that each one of my blocks is 8 nodes, and I have a job that's called A that requires all the resources on a single block. So stick it on this block here, launch it, it goes. But what's nice is this scheduler is running on our allocation, so it's not interfering with the batch scheduler. The scheduler says, oh, I just found a task called B. It requires 4 nodes worth of GPUs. Well, in this block here, I've got 4 nodes and their GPUs are empty, so stick them there. And C. Oh, I found another task that requires 4 nodes worth of GPUs. I have a block that has 4 open. Stick them there. And then, oh, this particular work, I found, maybe, these are linear solves. I found 8 nodes worth of CPU tasks. And I have a block that had 8 nodes of CPUs open. And I just laid them on top, right? And these guys are doing GPUs. These guys are doing CPUs together. these GPUs and these GPUs don't have to talk at all. Okay, I'm going to skip this for time. The thing that you have to tell MPI-JM is you have to tell it a little bit about your computer architecture. You have to tell it, okay, I have this much memory on a single node. These slots are CPUs. Those slots are the CPUs that control the GPUs, things like this. All information you can get out of the hardware locality command line stuff. And it's very simple to start or create a task. You can set environment variables, you can set arguments, you can say this job requires 24 CPUs, and say before the job starts, execute this Python command. After the job finishes, execute that Python command. Doing job prep and job cleanup, which is going to help us in the future. And so after you've created the job, you stick it in the queue, and at that point the scheduler can say, all right, I'm ready. Does it fit? Yes or no? Maybe if I get free space later that opens up, I'll stick it there. So here's our performance benchmark. This was on Sierra in preparation for a Gordon Bell application. And so we were scaling the number of GPUs and the performance that we were getting out total. And what this means is we were doing linear solves on a lattice that was roughly speaking this big. And what you can see is we were getting exact linear scaling. Okay? And that's essentially because when we say we're using 4,000 GPUs, really it means we're doing 1,000 tasks that require 4 GPUs or something. Okay? So it's just ensemble stuff. The red line here is with job management. The blue line is without job management. What that means is it was using many MPI run or MPI exec equivalent calls. This guy uses, the red one, uses just one MPI run or MPI exec. And so that's much more neighborly and stresses the resources on the head node much less. Okay. Yeah, so that's what I have to say. We're hoping to really be able to push this software and use it to extract science out of these big machines. And our plan is to make it widely available. It's already on GitHub, but it's probably still a little bit immature for users that aren't me and my collaborators. But we hope to have a real production-ready version soon.
Thank you very much.